Hi, Steve Dedenberg here with another AP Physics 1 lecture. In this lecture we are going to talk about force and acceleration and Newton's third law of motion. So just to start out, here's one of the most famous equations in all of physics. F equals ma. If you have a mass and you apply a force to the mass will accelerate. It will change its velocity according to the equation F equals ma. The mass of an object, just colloquially, is its inertia. If something has a lot of inertia, it's hard to make it move. And if something has a lot of mass, it's hard to make it move. If you apply a force to a mass that is big, if the mass is big, the acceleration is going to be small. And similarly, applying a force to a mass that's very small will produce a large acceleration. So the mass of an object is related to its inertia, and when we get to rotational motion, we explicitly call it the inertia of the object and not the mass of the object. So let's talk about the units of this. Force is measured in newtons. Force is newtons. But what is newtons? That's mass times acceleration. So the units of mass times acceleration are kilograms. That's the mass. And the acceleration is meters per second squared. So kilogram meters per second squared is the units of force. And that's newtons. Now, let's talk about gravity being an acceleration. If you have a mass, let's say the mass is falling off the edge of a cliff, that's a favorite problem, and gravity is pulling down on the mass, there's a certain acceleration, which is g, which is about 9.8 meters per second squared. And the force on this mass is its mass times the acceleration, which is g, okay? So the force is mg, and that force is being applied to the mass by gravity. But that's actually a different situation than what we talked about above with a horizontal force pushing a mass that has inertia to get a horizontal acceleration. In the case of the force pushing the mass along, you can apply any force you want to that mass and get any acceleration you want. A small acceleration, a large acceleration. Gravity, on the other hand, always provides the same acceleration, which is fascinating when you think about it. So gravity will change the force to get exactly the same acceleration for each object. You can push with a force of 10 newtons on a little mass and get a big acceleration, or you can push with a force of 10 newtons on a big mass and get a small acceleration. But in a gravitational field, if you have a little mass, gravity will provide a small force to create exactly 9.8 meters per second squared of acceleration. And if you have a large mass, gravity will provide a much bigger force still to get that same exact acceleration. And for this reason, there's a vocabulary term that you need to know for the test. When we're talking about a mass that is being pushed by a force that is not gravity to achieve some kind of acceleration, this mass is the inertial mass of the object. The inertial mass. And the inertial mass is the property of the object that has inertia, that keeps you from accelerating it despite the force that you're pushing on it. However, when an object is being pulled down by gravity and receives a force of mg, now we're talking about the gravitational mass of the object. And the gravitational mass of the object is the property that gravity grabs hold of to provide exactly the force to give it the acceleration 9.8 meters per second squared. So we never write it like this, but really, in this situation, if we're saying F equals ma, what we're really saying is the force applied equals the inertial mass of the object times its acceleration. And in this situation, what we're really saying is that the force applied by gravity, the gravitational force, equals its gravitational mass times its acceleration. Now, you don't really have to worry about these subscripts here, because as it turns out, as Einstein showed, the inertial mass of an object and a gravitational mass of an object turn out to be the same thing. They're measured in the same units, and for an object, they are the same. But that's a little distinction that you might come up to on the test. And just as one last thought on the difference between inertial and gravitational mass, let's say you wanted to provide a test. You're going to have a small mass here and a large mass here. We're looking down on them from above. And you're going to provide a force on this one and a bigger force on this one. And you're trying to get these two masses to accelerate at the very same rate and just be exactly parallel to each other all the way across the floor of your laboratory. Well, it would be almost impossible to control the force that well. Whereas, on the other hand, if you had a small mass here and a large mass here, and you dropped them off a building, you don't even have to do any work to get exactly and precisely the force applied to each of these so that they would drop with the exact same acceleration. So now let's talk briefly about Newton's laws of motion. We've really already discussed the first two laws. The first law says that a body at rest, or a body moving in unaccelerated motion, that is with a constant speed, tends to stay that way unless acted on by an external and unbalanced force. So what are we saying? If a body is sitting at rest and there is no force on it, or if there are forces on it but the forces are equally balanced and there's no net force, then the body will remain at rest. Or if the body is moving at a constant velocity in some direction and there are no unbalanced forces on the body, it will just keep moving in that direction at the same velocity. This will be the subject of some tricky question, perhaps, where they will say, a body has no net force on it. What can you say about that body? And one of the answers will be, it has zero velocity. It is at rest. But really what they want you to know that it could be at rest, but maybe it's also moving with a constant velocity in a constant direction. Then, Newton's second law says that if there is a net force on an object, it causes an acceleration to the object that follows the equation F equals ma. Now remember also that the force on an object and the acceleration of an object are vectors. And what that means is that the direction of the net force is the same as the direction of the acceleration of the object. The math of this, F equals ma, is usually not complicated in the AP Physics 1 class. You'll be given a body that has certain forces on it, and you'll compute the net force on the object, and that will tell you how to get to the acceleration of the object. Or perhaps you'll have an object that is not moving at all. Maybe it's suspended by various cables and gravity's pulling on it from a ceiling, and they'll want to know the tensions. You know the object is not moving, so all you have to do is add up all the forces and make sure that the forces are zero on the object since it's not moving. So the math is not going to be awful. And by the way, Newton was really, really smart. Wait till we discuss in a future video what he did with Kepler's laws of motion 70 years after Kepler. And you did notice, by the way, that the unit of force is called a Newton, right? Now, in the next video, we're going to talk about Newton's third law of motion, its implications, and how I can guarantee you a couple of right answers on the AP Physics test by understanding Newton's third law well. See you next time.